Logic plays an important role in the foundations of mathematics, while it turns out that it plays an important role in the foundation of physics as well. A physical theory, in the end, makes certain statements about the world, and their logical relationship, its internal logic, gives us the most fundamental structure. The difference is that these are statements about the world, things that we should be able to verify experimentally. So how do we capture this logical structure? What is the correct mathematical structure that we should use as a foundation for all our physical theories? How does it connect to the higher level mathematical structures we use in physics? Can we justify this structure from physical requirements? These are the questions that we are going to answer in this video. We will start from scratch and layer axiom by axiom, definition by definition, starting from the basic idea that we are describing a set of statements whose logical relationships can be fully defined by the possible ways these statements can be true or false. These statements may be associated with tests which may or may not terminate, and whose result will determine which statements are true and which statements are false. This will indeed take a lot of time, so let's get started. We're going to look at two sets of axioms. The first set I call the axioms of logic because they define the fact that we have statements, and statements must have a well-defined logical relationship between them. The second set of axioms, the axiom of verifiability, instead allows us to keep track of which statements are experimentally verifiable, which statements have associated tests, and what properties and what things we can do with those statements. And in a nutshell, the first set of axioms essentially recover standard logic, which mathematically is a Boolean algebra, and the second set of axioms recover what is called intuitionist logic, which is a hidden algebra. And a mathematician might just say, why don't you just assume that you have a Boolean algebra and a hidden algebra and be done with it? And that's the problem. We can't just assume that we have math. We have to show that our physical requirements lead to that math. Because while a set of statements fits the definition of Boolean algebra, not everything that fits a Boolean algebra is a set of statements. So we still need to know exactly what it is that we are describing, and just saying we have a Boolean algebra first of all, it doesn't tell you what actually you are describing, and second of all, it doesn't tell you why must you use that structure to be able to achieve that goal. So that's going to be our purpose. We go through these things, so we'll see why we do things in a particular way. First, we set up the logic, and then we set up the verifiable part of the logic. So let's start with the idea of a logical context. So the idea is that our statements don't just come out of nowhere, but they're all grouped together by what we call a logical context. So these are the things that we want to say. We're going to have things like definition. These are just mathematical definition. We are going to assume that there is a Boolean set, a Boolean domain that has two values that are false and true. And of course, the formal part does not know what true and false means. There is just two possible values for our logic. And what we would like to say is that a statement S is an assertion that is either true or false, and that a logical context S is a collection of statements with a well-defined logical relationship between them. And of course, if you start like this for a formal system, you talk to a mathematician, they're going to tell you, oh, this is not precise. What exactly is a statement? What is true or false? What does well-defined logical relationship mean? So again, this is the informal definition, right? This is where the physics live. This is where the real concept that we want to model exists. And then we have to take part of those ideas and formalize them into the math. So we're going to say that formally, a logical context S is a collection of elements, a set, and each element of the set is called a statement. And in this context comes equipped with a function that for each statement is going to give us one of these Boolean values. So each axiom, each definition that we're going to have are going to have two parts. The informal part tells us what elements in the physical world we are actually trying to characterize. And in what we are trying to characterize really here are statements about the physical world. And then there is a formal part that tells us how the elements are characterized by the formal system, how they are characterized mathematically. And each axiom and definition must have a justification, and that argues why the mathematical characterization follow from the physical one. And here, and if you want, you can go in the book and see exactly how we justify it, and then you can argue whether our justification is correct or not. But the idea is that we're starting from the idea that science is universally and non-contradictory, and so it must deal with assertions that have a clear meaning, a well-defined logical relationship that are associated with a unique truth value. And so that's basically what grounds us and what allows us to say, yes, we must have this collection of statements, and this collection of statements must be part of a logical context that defines the logical relationship and what is it exactly that we're talking about. So again, if we look at the relationship between the informal system and the formal system, an axiom is something that brings an object from the informal system to the formal system and specified what these things must be. Definitions instead are things that work within the formal system and further specifies formal objects. So you're going to have an axiom brings in a certain object, and then a definition says, oh, these parts are going to be have this additional property, these other things are going to have additional property. And the rule, how we choose axiom as definition, is because they are easy to justify, because they make sense physically. It's something trivial that we can write the justification for. In the same way that oftentimes you define mathematical objects in a way that they're easy to work with mathematically, to prove theorems or to do calculations. So here is not that different. It's just that what we need to do is different because our main goal is to justify those axioms. So again, if we just said, oh, we have a Boolean algebra, that's much more difficult to justify. We just say that there are some statements and there is a logical context, and these statements must be either true or false. And so what we shouldn't be doing is follow trends in mathematics. A mathematician comes in and says, I don't know, axiomatic fact theory, that's what you should use, or category theory, and so on. Well, all of those things are good for doing math in a way that a mathematician wants to do, but if we have to do math in a way that we need for physics, we need to start from things that are justifiable for the physics and they work at that level. So, okay. Another thing that is important when we go from the informal system and the formal system is that physical objects are fuzzy. We're never going to be able to take a physical object and really fully specify everything. So even when we say the mass of the electron is, I don't know, less than 1 gram, there is a lot to unpack there. We need to exactly define what an electron is, what a gram is, and so on. And all these definitions, as we saw in a previous video, will have a little bit of hand waving. Exactly, when we define a gram, we are never defining it to infinite precision, yet we talk about infinite precision and so on. So what's happening here is that physical objects are made mathematically precise, they're made crisp. We have objects that these statements are really always true or false, they're never ambiguous. And the way that we can do that is essentially by throwing out all the things that can be made precise. So if we actually had to stay there and define exactly the meaning of each statement that we have in a physical theory, things like formally, not just in words like we do, which is absolutely fine. No, formally, that we have to define exactly what an experiment is, what an electron is, what grams is, it would be a total mess. And so what we do here is that things like the syntax, the grammar, the meaning of each statement, since cannot be made precise in a way that it's formally precise, that it's good enough for math, what we do is just leave it outside of the formal system. So from the perspective of the formal system, the statement is a primitive object. It's not decomposed in predicates, subjects, and all of that. No, it's just one thing as it is. And from the informal system, we say that these things exist and they have a well-defined true and false value, and sort of the formal system accepts that as the starting point and as an axiom. And so the statements in this system are the primitive objects, and no statement is more primitive than the other. You just have a bag of statements. What these statements mean formally, the formal system does not know. So, and here is something that I sort of bumped my head over and over with mathematicians because while trying to make this thing precise, when I would go to mathematician, they would always complain, "Oh, it's not precise, it's not precise." And a lot of the time, precision in mathematics is really just a matter of following conventions. And so in mathematics, the primitive objects, the ones that are left unspecified, because in every a formal system, you're going to have primitive objects, things that are taken as is and they are not specified. But the convention is that these must be elements of the set. So if I just went to a mathematician and said, oh, there are statements and then statements form a logical context, they're going to ask you, well, what exactly is a statement? But if you say, oh, I have a logical context, which is a set, and the elements of the set are called statements, suddenly this fits the pattern, the sort of the rules of how you do formal math, and this is a lot more acceptable. So the logical context here, and this axiom is defined like this for these two essentially reasons. The logical context have these two functions. In the formal system, it is the container for the primitive object, the statement, so that we can rely on the standard formalization through set theory. We basically just say we start with having a set, and the set is the context, and the elements are the statement. And so that follows conventions, and we can talk to mathematicians. And in the informal system, the logical context in the informal system instead basically binds together the idea of consistencies and semantics, because these are really defined on groups of statements. So it's the context that tell you what an electron is or what is not, what a dog is. Are we talking about animals, about cartoon characters, right? All these things would be different, and it's the context, the logical context that specifies, oh yes, this word in this context means exactly that, and that is why you have these logical relationships. So there is this double function, and again, this is just to tell you that even when we just write definitions like this, it's because they survived multiple iteration and they just work for a particular reason. This is it's not at all random. Everything that we have in our book, where we have all this axiomatization, all the words are chosen so that some of these issues are solved in a way that feels natural, and so you don't have to think about these things. So another thing that is important to specify, the statement here represents the assertion and not the sentence that declares the assertion. Therefore, the translation of a sentence into another language represents the same statement. So if I say that animal is a bird or quell'animale è un uccello, then these statements, these two sentences are the same statement because they're actually saying the same thing, just translated in another language. And it kind of makes sense that we want to have the basic objects not to be a sort of language dependent, right? It has to be sort of the conceptual things. And again here, technically we only assume the existence of valid states for doing science, and therefore statements are also primitive in the informal system, but so basically meaning that we're not even assuming technically that we can do science, that there are such things as a statement that are really true or false, meaning, for example, one of my favorite examples is talking about oranges. It seems very clear that either something is an orange or not, but if you think of how an orange grows, it starts with a pollinated flower, and at some point it becomes an orange, and there is no point where you can say, oh yes, that's point, from this instant on, it's an orange, and before it was not. So there are always things that are murky, and there are some people in philosophy that argue, oh no, science is impossible, or whatever. We can even stay away from the debate, because we basically say, well, we're not saying that we can actually have propositions that are testable. We're just saying that if we have propositions that are testable, they're gonna have to follow this structure. And of course, then we find propositions that follow this structure, and therefore we can do science, and therefore the saying that we can't do science is nonsense. But again, technically, and again, this is because we want our formal system to rely on the minimum set of assumptions possible. So technically, we're not even saying that these statements actually exist. We're basically saying that if they exist, and then they must follow this pattern, and therefore they must obey this mathematical structure. So again, we save ourselves from some possible attack. So the existence of a true function stem again from the assumption of non-contradiction and universality. For each statement, we must know whether it's true or false. And it must be so for everybody. It's not like, the fact that chocolate is good or not, that depending on who you ask, you might get a different answer. No, chocolate in this particular time is made with this particular characteristic, then chocolate is brown, or chocolate or dark chocolate is darker than milk chocolate, then those would be things that are more objective. And so you can really think as the context at the end of the day, after we remove all the things and all the details, the context is just a big table. Every column is a statement, and then at this moment we just have one row, and the row is the truth value for each statement. So that's essentially what we are trying to capture, just a big table. And these are the type of statements that we're going to have in a logical context, just to make it concrete. So let's say we're talking about particles because we're talking about physics. And so this is going to be a bag of statements about, for example, the mass value of the particle. So the mass of the photon is greater than or equal to 0 electron volt. This would be a statement. The mass of the photon is negative. That's another statement. Again, statement doesn't have to be true or false. They just exist as statement. And then you say this statement is true, this statement is false, and so on. The mass of the photon is less than 10 to the minus 13 electron volt, or the mass of the photon is exactly 0, or something like the mass of the electron is 510 plus or minus 0.5 kilo electron volt. So you're going to have essentially a bag of all these statements, and that's what we have for now. But of course, this is not enough. We want more. We want to add some structure to this. And so what we want to do is represent this logical relationship between statements. That if one is true, then the other one must be false, and things like this. And the semantic content is really what constrains a possible combination of true values. So for example, suppose that we have a context, and in this context we have these three statements: so that animal is a cat, that animal is a mammal, and that animal is a bird. Now, these are all the possible combination of true value that in principle three statements that can have, but these three particular statements can't just have any combination. All these things cannot be true because something can't be a cat and a bird, or something cannot be a cat but not a mammal, and so on. So all these combinations are impossible assignment. We can't assign these particular truth or falsehood of values to this particular statement. And it's the semantic that tells us. It's the fact that I know what a cat is, and I know what a mammal is, and I know what a bird is, that makes me say, you know what, this is not possible. And as we said before, the formal system does not know about the semantic, just know that there are these statements. And for the formal system, these are labels. It doesn't know what they are. It's like, the formal system does not understand English, therefore for the formal system, these are just a string of characters, and the formal system can just see, oh, these characters are different, but is not able to know anything else. And so what we want to do is capture these possible assignment, and this is the only part of the semantics that is going to be captured for the formal system. So the formal system is not going to know what a cat and a mammal are, and what a bird is, but it knows that it can't assign true to all these statements. That's it. So how do we represent this formally? Well, given a set of statements, we define an assignment, something that associates a truth value with each statement. And so basically we have a function, an assignment is a function from a set of statements, from a context, to true or false. So if this is our context, and all the columns are a statement, an assignment is just a row, and for each column it tells us whether the assignment is true or false for each statement. So you might have an assignment on the full context. You might have an assignment restricted only to a few statements because those are the only statements that you're considering right now, or you could have an assignment for a single statement and at that point it's just true or false. Again, not rocket science, and now that we know what assignment is, we can define an axiom. And the axiom we basically says it's the axiom of possibility, and it tells us that a possible assignment for a logical context is a map from the context to a Boolean value, so true or false, that assigns a truth value to each statement in a way that is consistent with the content of the statement. And of course, this is the informal part. This is what it means for us a possible assignment. And for the formal system, well, a formal system, we just say that a logical context comes equipped with a set of all possible functions, such that, not of all possible functions, a subset of all possible functions, and the truth is one of these possible assignments. And so, again, if we want to just represent it visually to understand what this abstract definition means, it's just, well, the context is really a full table, like this. Each column is a statement, like that animal is a cat, that animal is a mammal, the mass of the photon is greater than this value, it's between these values, and so on. And a possible assignment is just one of the rows. So all the rows that we have are things that make sense to assign to those statements, and the truth is one of the assignments because the truth must be a possible assignment, otherwise our model makes no sense. And so really we can understand the context as a big table where the statements are column and each row is a possible assignment. That's the thing that we're trying to model mathematically. That's it. There is really nothing else. That's kind of the neat thing. We get a simple structure and we're going to get a lot of things from it. Okay, so right away we can say that there are three kinds of statements. There are things that are certainties, meaning that in every assignment they're true. So if I say that cat is a mammal, well, of course, that's always going to be true. So that's a certainty. We have an impossibility, which is a statement that it's always false in every assignment. So that mammal is a bird. Well, that doesn't work. It's always going to be false. And then there are statements that are contingent because they're never certainty, never impossible, because they get different values in different possible assignments. So if I say that mammal is a cat, well, I don't know. I have to go and look, see what mammal are we talking about. So sometimes it could be true and sometimes it could be false. And that's it. So you can see that, again, it makes sense that these things are certainties and these things are impossibilities, but you see that these are definitions because they are further specification of the things that we have brought in from the axiom. Knowing that there is a context, knowing that there is a possible assignment is enough to define this concept within the formal system. And that's kind of what you want to do. You want to minimize the set of axioms and to be able to create as much of all the other intuitive ideas that you want to have them as definitions. Okay, so one of the things that is important here is that whether a statement is certain or contingent depends on the context. So if you imagine the statement, the mass of the electron is 510 plus or minus 0.5 kiloelectron volt. Well, this statement is a contingent statement if we don't know what the mass of the electron is and we are going to go and measure the mass of the electron. It wouldn't make sense to go and measure the mass of the electron if we already knew what the mass of the electron was. So in that context, when we go and perform that measurement, well, then the mass of the electron has to be not known, and therefore the statement must be contingent. But if you are in a particle accelerator and you make particle collides and you don't know what particles come out, and you have to identify, you have to say, oh, that particle is an electron. You're going to be able to say that it's an electron because the mass is going to be within that bracket. So in that context, when you're doing particle identification, then that particular statement is no longer contingent, but it's a certainty. It's inside this context, we're assuming from previous experiment that that statement is true, and that's how we can distinguish electron from proton or quarks or whatever, but we can't distinguish them, for example, from positron. For positron, we would need something more. So again, this should tell you that physical theories are, or essentially when we model things, the context is important because it defines this possible assignment. It defines what we think we can find or not find, and depending on what we're doing, we might assume something that before we were, trying to figure out whether it was true or not. So, for example, in relativity predicts the Doppler effect such that the wavelength changes depending on the speed of what things are going. And again, if you are testing special relativity, you would test whether the Doppler effect actually works or not. So you fix the velocity of a target, and then you measure how the frequency changes, and you say, aha, the Doppler effect exists and it works like that. But then you can say, well, I know that the Doppler effect exists and I don't know what the velocity of the target is, so I use the Doppler effect to know the velocity. And so whenever you are in a context, the role of what is sort of the fixed set, what are your certainties and what are the things that are contingent that you have to figure out, changes role. And again, this is important to see that this is different, and this is exactly the type of work where layering in all the assumptions, you understand that there are these assumptions that you're making. And so this is, for example, important because if you want to say, I want to do a theory of everything, what does it mean? What does it mean in terms of which statements you're taking as certainty, as contingent? Can you really have a context where everything is exactly certain and contingent always in the same case? It's not clear to me that that makes sense. So again, let's think clearly and go through all these details. Okay, the other thing that we want to analyze is dependency from one statement on the other. So we have all these statements, and we saw before that not all those things can be true at the same time. So for example, if we say that that animal has feather and that animal is a bird, well, these statements are equivalent because what happens is that all the living animals that have feathers are bird, and all the birds have feather. Now, if you went to historical times and looked at dinosaurs, some dinosaurs had feathers, so this wouldn't be true. But if we're talking about current animals, that this is true. Sort of having a feathers is the defining characteristic of birds. So these two statements are equivalent. These two statements are incompatible because if something is a bird, it's not a mammal. This statement is narrower than the animal, meaning that if I know that that animal is a cat, that animal is a mammal is true as well. Like this gives us a narrower, more refined description than this statement. Then these two statements are independent because if I tell you that the animal is a cat, I don't know whether it's black or not. And if I tell you that it's black, I'm not telling you anything of whether it's a cat or not. And that animal is not black is negation. So this is exactly true when this is false and vice versa. And the cool thing that the possible assignment fully determines this type of relationship. So we don't need to put anything else in the formal system. We can just look at the possible assignment and define this relationship. So for example, the fact that these two statements are equivalent, meaning that they can be both true at the same time, that they can be false at the same time, but they can't be different. So if you look at all the possible combinations, we only have these two combinations. Or the fact that they are independent means that we can have all the possible combinations. So if we look at all the possible assignment, we are going to have some assignment that in which any of these four things can happen. Or if two things are incompatible, like the mammal and the bird, then they can't be true at the same time. So this condition must be ruled out. And so this is what we're going to do. We're going to define all these relationships based on the axiom that we already have. So again, these are definitions and they're not going to be axioms. So we can say that two statements are equivalent if formally the assignment is the same for all the possible assignment. So for example, these two statements are equivalent because, as you see in all these lines, the truth and the falsehood is exactly the same. And by this definition, what we can show is that all the certainties are equivalent and all impossibilities are equivalent, because if S6 is a statement that it's a certainty, it's always true, and S7 is a certainty, it's always true, then they're always true at the same time. They can't be different, and therefore they're going to be equivalent. What you can show is that this statement equivalent has these three properties. It's reflexive, meaning that a statement is always equivalent to itself. It's symmetric, because if S1 always have the same value of truth value of S2, then all the truth values of S2 are always going to be the same as S1, so it's symmetric. And it's transitive. If S1 is equivalent to S2 and if 2 is equivalent to S3, then they're equivalent. And therefore, this in set theory is an equivalent relationship. Essentially, the whole context now can be broken apart in all these subsets of statements that are equivalent to each other, because they have always the same truth value in all the assignments. And this shows that we have essentially three types of equivalent relationship among statements. Three things that you can say, oh, these two statements are the same. So two statements could be the same because they are semantically the same, as we saw before. So swans are birds, and I cigni sono uccelli. This is the same statement, and therefore these are the same objects. These are not two different things. Even though they are two different propositions, the way that we express the statement is different, the statement is really the same. And in logic, this is called the semantic equivalent. These things semantically mean the same thing. Then the other equivalence that we define now, the fact that things always have the same truth value in all the possible statements, then this is called the logical equivalent in logic. And again, the examples that we have is swans are birds and swans are feathers. These are two different statements because these two things mean different things. The fact that they have bird is the fact that something comes out or is attached to their skin. The fact that they have feathers is something that there's something attached to their skin, and then the birds is the fact that they have a particular classification. So these two technical are two different things, but if one is true, the other one is true. If one is false, the other one is false. And then you could have two things that happen to be true at the same time. And this is called material equivalence because they have the same material, the same value that they have. And so swans are birds is true, the earth is round is true, and then both of these are true, but of course they have no relationship with each other. And the thing is that what is nice about this system that we have created is that we can distinguish between these three cases in the same framework, and that's useful because, again, conceptually you can see, aha, look at that. Those three things are different, so we can keep track of them. And now, as I said before, the context now can be thought about this divided into this collection of statements that have the same truth value, and that essentially defines the elements from which we can actually have this logical relationship. And so what we are going to when we talk about statements right now, we are going to talk about this equivalence class. We're going to make, we're going to collapse this statement into a single thing. We are going to call the statement the fact that we have one of these two statements, because at the end of the day, that's where the logic works. There are going to be some cases in which we might want to make the distinction, and we can if we need to, but at the end of the day, it's statement equivalence that it's important to us. So for us, a statement, it's one of these things that always have the same truth value in all the assignments. Okay? Given that, we can say that a statement is narrower than another if whenever one is true, then the other one is true as well. And this is, the animal is a cat is narrower than that animal is a mammal. And broader is exactly the opposite. So that animal is a mammal is a broader statement than that animal is a cat. And for example, if we again look at the truth values, this is always true whenever this is true. Sometimes this is true when this is false, but that's okay. And so S2 is narrower than S3. And two things are compatible if they can be true at the same time, so that there is an assignment such that both things are true. So for example, these two statements can be true at the same time, so these are compatible. And of course, you can see that all these four statements that can all be true at the same time, so they're all compatible with each other. Okay? So again, we can say the compatibility is, for example, that animal is a mammal is compatible with that animals that lay eggs because there are platypuses, and platypuses are mammals that lay eggs. So there is a case in which these two things are the same. And as I said before, narrower, we can think of cat and mammal as being one narrower than the other. One of the things that we can do now that we have this narrowness, and it sort of should tell you that we picked a symbol for narrowness that looks like a less than. And we picked it because we can show that narrowness forms what is called a partial order. For a partial order, you need three things. You need reflexivity, so that S is narrower than itself, or if you can think a number is less than itself. You need this relationship to be antisymmetric, such that if S1 is narrower than S2, then S2 is narrower than S1. Then if both of these are satisfied, then you have the same statement. So if S2 is true when S1 is true, and S1 is true when S2 is true, then they're equivalent and makes sense. And then you have transitivity. If S1 is narrower than S2 and S2 is narrower than S3, then S1 is narrower than S3. So if S2 is true when S1 is true and S3 is true when S2 is true, then of course S3 is true when S1 is true. And this essentially is the structure of partial order. And these are this basically is what brings in order theory in all this idea. But before we look at that, one of the things that I want to point out is if you did logic, it would look like narrowness is essentially material implication, because I'm saying if something is true, then the other one is true, then there is this implication. We're not using the same symbol because material implication in logic is really a logical operator that returns another statement. So saying A implies B is the same statement as saying that either I have not A or B. And we're going to look later what these expressions are, the not and the or, there's a logical operation. But the point is that material implication, these symbols, typically gives you another statement. It takes two statements and creates a new statement. And that's not what's happening here. Narrowness is just a binary relationship. So you give it to statement and it tells you whether, doesn't give you another statement in the logical context. It just tells you whether that thing is true or false. Right? It's just a relationship between the assignment. So that's why we have a different symbol, because it's not exactly what people do in standard logic. Okay, but one of the important things that here is that the order imposed by narrowness allows us to understand the context as an order theoretic structure, and this is one of the nice things. So we start with a table, right, with a table of this assignment, and now we can define this this relationship, and with this relationship we can look at the same thing in a completely different way, and sometimes it's useful to look at things in a completely different way. So for example, let's assume that you have the logical context for a traffic light, right? And so we have three statements that the traffic light is green, the traffic light is yellow, and the traffic light is red. And then we have other statements that the traffic light is green or yellow, green or red or yellow. And we also add an impossibility here and a certainty here. So a certainty could be the traffic light is green or yellow or red. It's always one of those three. Or the impossibility could be the traffic light is green and yellow. That cannot happen. Sorry, so that statement is impossible. Okay, so this represents all the possible statements that we are going to have. The statement where something is impossible, so the statement that is always false. The statement that either we have green, yellow, or red, so it's true in one case. And these statements, green or yellow, green or red, red or yellow, these are true in two cases. And then the fact that the traffic light is green or yellow or red, this is always true, and it's true in all three cases. And so these statements now are ordered by narrowness. The impossibility is true in fewer cases than A, and whenever A is true, X is going to be true, because if it's green, then of course it's green or yellow, and so on. And so we have these statements that are ordered, we draw them, this is called a Hesse diagram, because we have all these points, we have a line that connects these statements that are narrower, we are strictly narrower from one to the other, such that we can, and then we order narrowness with, from bottom to top. So we know that this is broader than this is broader than this, and this is broader than this. And this statement is broader than these two, and this statement is narrower than these two, but there is no relationship in terms of ordering between this and this. We can't say that A is narrower than Z, because when A is true, Z is actually not true, because if the traffic light is green, then it's not going to be yellow and not going to be red. So this is another way that we can represent these statements. Instead of putting them on a table, right, we would have 8 columns and we would have the 3 rows depending on what case we have, and have all the possible combination of the assignments. And we can also represent it in a diagram like this. And we have this notion of ordering. And what is interesting is that this notion of ordering, actually, that we have on statement, it's going to rederive the notion of ordering that we have, among integer or real numbers and so on. So that those notion of orderings that we put on objects can be seen as essentially ordering on the statements about those objects. And of course, this would be a topic for other videos. But what I'm saying is that we have found this very straightforward to define this structure, and this structure then can sort of percolates up the other physical structure that we're going to be interested in. But now we know where a fundamental level comes from. Okay. So enough about that. There is one last logical relationship that might be interesting, which is the one of independence. If I say that the animal is a cat, then the fact that the animal is black is completely unspecified. And this, as we said before, is just means that we can have all the possible permutation in terms of truth value. Now this becomes a little bit complicated to define, but the thing that is important is that independence is really defined not just among two statements, but among a set of statements, a little bit like linear independence, which is a cousin of this notion of independence. It's really defined on multiple things, because you can have A independent from B independent from C, but then A and C actually be dependent with each other. So that's why the definition, the formal definition, is a little bit more complicated. And if you want, you can stop a video and look at it. But that's kind of my point. The point that I was trying to make here is that you can define the notion of independence from the axioms that we had before. Okay, and so if we look at our example of logical context about the masses of photons and electrons, so that we can sort of understand the fact that the mass of the photon is greater than or equal to 0 electron volt, this is a certainty. The fact that the mass of the photon is negative, this is an impossibility. The fact that the mass of the photon is greater than or equal to a particular value is broader than the fact that it's just greater than that particular value. The fact that the mass of the electron is something and the mass of the photon is something else, these are two independent statements. The fact that the mass of the photon is exactly one value and exactly another value, then these statements are incompatible, because if one is true, then the other one must be false. Okay? So what we've basically done with these assignments, we have created a lot more structure to this, and we saw that these logical relationships are based on the truth value. If you just know the possible assignments, we can define all these relationships, and we have this idea of things being broader and narrower so that we can put an ordered structure on this context. Okay? But this is not enough in terms of statement dependence, because sometimes you really want to say that a statement, the truth value of the statement is fully determined, depends on the truth value of some other statement. So if I say that the animal is black, right, and I say the animal is not black, well, if I know the truth value of this, well, that's enough to exactly determine the truth value of this. So there is a function that links the truth value of one statement to the truth value of the other statement. And that function is the negation. If I say that this is true, this is false, and if I say this is false, this is true. Okay, so the idea is, again, that the possible assignments determine this statement dependence. We should be able to just look at the assignment and say exactly whether and how one statement, the truth value of one statement, depends on the truth value of other statements. Now, defining this formally is a little bit tricky, but essentially this is how it works. You take your logical context, you have all your possible assignment, and let's say that we pick three statements, and again you can think of this being cat, mammal, bird. It doesn't really involve the statement they are. And so formally we have an FB, which is a function from Boolean values, and in every assignment, if we look at the assignment, the value of S bar for that assignment, this is equal to applying the function, the Boolean function, to the value of the statements for that particular assignment. And so this is going to be true for all of them. And if this is true, then we say that S bar depends on S1, S2, and S3 through the function FB, right? So this is what it means to be dependent. Now, one of the things that we don't know yet is whether you can always find a statement that depends through some function on any set of statements. And that's why we add this axiom, which is called the axiom of closure, that basically says whenever we have a set of statements and we have an arbitrary truth function, something that takes a Boolean value and gives us a Boolean value, then we can always find another statement that depends on those set of statements through the F. So we can basically take any statements and combine them however we want and get another statement. Now, technically, it might be that this does not need to be an axiom, because it could be that the closure always exists, so that if you have a logical context that does not satisfy the closure, you can always create one that satisfies the closure. And since we're assuming that in principle this could be an infinite set, because we need this with an infinite set, and I am not a mathematician and I'm not really quite sure whether this works on infinite set, and all the mathematicians that I talked to have been reluctant to assure me that this construction can be extended to all possible infinities and whether there are caveats or not. I just keep it as an axiom because I'm safe. If somebody would come and say, oh, look, I do foundations of mathematics, you don't need this axiom because of blah, 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 this is how you do it, I would be happy to throw out an axiom and be done with it. But for now, I'll just keep it as an axiom. We can always apply any Boolean function to any set of statements and be happy about it. And since we can do that now, what we can do is, given any set of statements, we can create now a function that goes from the particular statements to the statement whose truth value is related to the other statements through the function itself, right? So, for example, suppose that we have the negation. The negation here is going to be a function that taken a Boolean value gives us another Boolean value. So if the argument is true, then the result of the negation is false, and if the argument is false, the negation is true. So this is a function on Boolean values. And now what we want to define is a function on statement. We want to be able to say that the statement, that animal is a cat, if I negate it, I find that the animal is not a cat. And now this is a function on statements. I give you a statement and you give me another statement. And because of the axiom that we have to put, right now we can say, okay, we take this statement, and this statement is going to have a set of truth values. We have a function, a Boolean function, which is the negation. We are going to find the corresponding statement such that the truth values depends on this through negation, and then there is a statement here, and we say this statement is the negation. Okay, so we go from a function on truth values to a function on actual statement. And in the same way that we can do it for not, we can do it for any Boolean function. So we can have an AND, a conjunction, and if the AND is true, if and only if the two arguments are true as well. And so if we take this statement, we make the logical AND. We can, the conjunction, we find another statement in the context that is the conjunction of the two. And again, notice that we're not constructing new statements. We are going to find a statement within the set. This is a little bit like when you define addition in natural numbers. You have the set of natural numbers, and then you have addition that takes two elements in the natural numbers and give you another one, right? So it's a map within elements of the same set. So this is the same thing for us. The AND is not constructing new thing, it's just finding things within the context. In the same way that we define the conjunction, the logical AND, we can define the disjunction, the logical OR. In terms of Boolean functions, the OR is the Boolean of the AND, which is false only if both arguments are false and true otherwise. And again, here we can find, given two statements, we can find another statement that it's the disjunction. So if we say that animal is a cat and that animal is a dog, we are going to find in the context a statement that says that animal is a cat or a dog. Okay? Again, I want to stress that and, or, and not are operation within the context. They return other statement. You give me a statement, I give you another statement. But things like equivalence, narrowness, and compatibility are not statements inside the logical context. They are describing relationship within the context. These are part of the meta language. These are not statements expressed inside the context. So verifiability of the statement is completely ill-defined. It doesn't make sense because the only thing that we are going to apply verifiability to is on statements that are in the context, not outside the context. And this is important because essentially our context is not going to allow meta statements. So things like the photon, the mass of the photon is less than 10 to the minus 13 electron volt. That's a statement in the context. And can the photon have a mass that is less than that, which would be a statement of possibility, let's say. That's not a statement in the context, that's a statement about the context. So these meta statements are not in the context. And so physical theories are not closed through this sort of going up of self-reference. It's not there. And that's how you sort of avoid a lot of incompleteness problems. You really can't do those operations. They don't make sense at an experimental level anyway. Okay, so now that we have this, we can go and we look again at the example of logical context. We still have our those statements. We had the relationship that we had before, but now we can add the fact that two statements are related by negation and that three statements are related to disjunction. Okay, so basically that's what we had. We were just describing a table, and this table allows us to define all these nice things without really saying more than there is the table. So all these things at the end of the day, they're describing possible assignments and relationship statements based on the value of those tables. And this is how now we can recover the standard logical structure for logic. So we have defined our ands, our ors, and our not. And we can go and verify that these ands, or, and nots have these properties, and therefore they are Boolean algebra. By definition, the Boolean algebra is something that satisfies these properties, and what we define satisfy these options. So we recover the fact that we have a Boolean algebra. And again, if you're a mathematician who says, this is a lot of work, why didn't you just say that I have a Boolean algebra? Well, so not how many things I should have justified if I had a Boolean algebra. If this were my starting point, I would have to tell you why I want my statements to satisfy these things. And I wouldn't have the sense that these things are just talking about ways that things can be true or not true within the model that I have been defined. I would be completely clueless of what would happen. So we would have to do a lot more conceptual work in trying to show that those things have to be true, and I still wouldn't know exactly what it is that I am describing at the end of the day. And what I'm describing, as I said, is just this table. Each column is a statement, and each row, it's a possible thing, a possible assignment, possible way that those things could be true or false. And that's about it. And everything that you can show, because of the axiom that we showed before, is that all these operations actually generalize to the infinite case, and therefore the logical context is not just a Boolean algebra, but it's a complete Boolean algebra, and so you can do more operations. And so what is important to me is that we have three ways to look at this logical context. We have the truth table, with this column, there are statements that there are possible assignments. I've repeated it so much that hopefully that stays. And I think this is the most direct way to relate to logic and to relate it to what it is that we are actually modeling in terms of physical theories. Physical theories, we're going to have a bunch of statements about the world, and the bunch of statements about the world better have a good physical model such that we can define all these possible assignments and what is it that can be true or not be true. Then we can see this as a partially ordered set in terms of ordered sets of element binariness, as we saw before. And things like order structure, as I said before, when we have ordering on numbers, that ordering actually is, let's say, a projection of this type of ordering from the logical structure. And also when we're doing simplest composition and decoupling, you can see that these things can be understood as a partially ordered set, and sort of because they inherit this structure. The statements about the parts and about the whole inherit this structure, and therefore you can sort of see this thing. And the fact that we have the third way is the thing that we had just before, that we have an algebra, the Boolean algebra. And so these are a set of elements together with some operation, the and, the or, and the not. And this way of looking at the algebra relates actually more directly to the topologies, which means also geometry, probability, measure theory. All these things the direction can be sort of seen better in terms of this algebraic structure. But the point is that we don't have only one structure, we have multiple, and we can use the one that is more convenient for different things, and at the end of the day we're just looking at a table. So just to relate the algebra lattice structure to the order theoretic structure that we had before, to relate to the algebra is the algebraic structure and the lattice is this order theoretic structure, we have the same set of statements that we had before. This is, again, as before, these lines imply that one statement is narrower than the other. I also added these gray lines that are the negation. So this is the negation of this, this is the negation of this. and the certainty is the negation of the impossibility. And what you can see is that if you have one structure, you can define the other structure. So if you know that you have the ordering structure, for example, you know that this is broader than this and this is broader than this, but you do not know what an OR is. Well, what you can do is you take two statements, you find all the statements that are broader than those two statements, and then you find the smaller one. So for example, if I pick these two statements here, this is broader than both of these, and this is also broader than both of them because it's broader than this. Right? So if I take the set of all the statements that are broader than these two, I have these two statements. And now I take the narrowest, which is going to be this, and this is exactly the OR, the disjunction of these two statements. And so if I give you the order theoretic structure, you can get the algebraic structure. And you can also do the opposite thing. If you know the algebraic structure, you can define the order theoretic structure by saying if Q and P, if Q or P is equal to P, then Q is narrower than P. So for example, you can look at A and X, and you can say that if you do A or X, right? Well, this is going to be broader than both statements because something is broader than itself. So this is going to be the narrowest broader statement of the two, right? And this is exactly because this is broader than this. So we exactly have the same definition. From one, you can really derive the other. Of course, I wouldn't expect you to go and fully understand this in detail, but the point that I want to make is that all these structures are related to each other, and if you really want to understand all that is going on at the upper level, you kind of have to have an understanding of these things, because these are the things that are going to percolate through all the structure of physical theory. Okay. The last thing that I want to talk about for function is the fact that functions in Boolean algebras have a standard representation that is important to us because it essentially allows us to go from assignments to statements. And so the idea is that suppose that we have these three statements, S1, S2, and S3, and then we have a function S bar that is a function of these three statements. You can see that I could fully define S bar by telling you in which assignment this statement is true. Right? This S bar is exactly the statement that is true in the second, the fifth, and the seventh assignment. So how can I express that? Well, what happens is that if you pick three statements, you can construct what are they called a min term. A min term is essentially a statement that picks an assignment that is true only in one of these combinations. And the way that you can write it is a min term is essentially expressed as the conjunction that takes all three statements only one time, either negated or not. So for example, M1, well, the first line is the line where all these three statements are false. Therefore, the negation of these three statements are true. And so M1, the statement that is true only in this condition, is exactly the conjunction of not S1, not S2, and not S3. And so you can make all these combinations. You see here you have the false, true, Here you're going to have not negated, not simple, and so on. And so these represent all the possible combinations that you would have here. And so each of these statements here that can be expressed as min terms of these pick out a single line. So now we can express identify a single line by identifying it with a particular statement, which is the statement that is true only in that possible assignment. And then if I have any function of these three statements, then what happens is that I can simply say, well, S bar is going to be this line, so M2, or this assignment, therefore M5, or this other assignment, which is M7. So this is M2, this is M5, and this is M7, and therefore S bar is this, or this, or this. And this is called the disjunctive normal form. And this is going to be very useful later when we want to go from a sort of statement representation of all these things to a set representation and recover things like topologies in sigma algebra. This is exactly the way to do it. It's how you find the point, how you find the thing. So I just want to highlight it just because this is another important structure that plays a role, even though we're not going to see exactly how it works. And this is going to be the formal definition. If you want to pause it and look at it, there is a certain amount of cleverness of defining this operation such that this assignment is exactly the assignment in which the statement is going to be true. But anyway, it's just a formal definition that allows you to do certain manipulations. So this is essentially all that we want to say on the axiom of logics. Again, big table of things that allows us to have a bunch of statements which we don't know what they are, but we can define a logical relationship. And now we are going to finally reach the second part, which is adding the experimental verifiable part of all this logic. First, we should give a few examples of what we consider a verifiable statement and not a verifiable statement. So some statements are not verifiable statements simply because they are not statements themselves. So something like chocolate tastes good, this is not a universal proposition, it's not true or false for everybody, so it's not a statement. Things like it is immoral to kill one person to save 10, well, first of all, it's not universal, but even if it were universal, the issue is that morality is not evidence-based. You can't say, oh yes, this thing is moral. I go in a lab and I test whether the statement is moral or not. That does not work like that. The fact that numbers are prime or not, that's also not evidence-based. That is a statement. The number 4 is prime is a statement. It happens to be false, but it is not evidence-based as well. We don't go in a lab to see whether the number 4 is prime or not. We just follow the definitions. Something like the statement is false is not non-contradictory, so it's not a statement at all. And then there are things like the mass of the photon is exactly 0. These things that you might think, oh, it's verifiable because it's connected to experimental evidence. Well, it's not verifiable because of the infinite precision. We are never going to be able to say that the mass of the photon is exactly 0. What we're going to be able to say is something like the mass of the photon is less than 10 minus 13 electron volt. That we are able to say, in fact, we know it is true because experimentally we find that it's true. But again, it's because we have this error bar that we're able to say this statement is verifiable. And all the things that we verify in practice are a statement that have some imprecision to them when it comes to to real numbers. So we can verify something that, like, if the height of the mercury column is between 24 and 25 millimeters, then its temperature is between 24 and 25 Celsius. And again, this is also tricky because we are testing a dependence of one thing to the other thing, which is not just measuring the fact that those two conditions apply. We have to measure that whenever something whenever we have the first proposition, whenever we measure that the height of the measuring column is between 24 and 25, we have to always have the temperature is between 24 and 25 Celsius. And again, saying exactly how and when, under what conditions, a statement like this is verifiable, it's not going to be part of the formal system, because again, there are things. At some point we say, yeah, we tested enough conditions, we are satisfied, and we say that the thing is true, right? But all these, whenever you have induction, whenever you have sort of experimental settings and so on, saying that something always happen, you can't test always. So again, you are gonna have some uncertainty also on the conditions in which that statement applies. But again, you're going to say, okay, that we are satisfied that that is true. And the same thing if we do decay, we are going to measure that a particular fraction of something decays if we wait for some particular time. But again, there are going to be brackets, intervals. That's what we measure. We never measure absolute infinitely precise value. We measure intervals if a real number. So those are what we mean by verifiable statements. We need something that we say that there is a way to measure these things. And again, it's going to be a primitive notion. The formal system does not know exactly what that means. Even defining this in an informal way is oftentimes difficult and full of caveats. But again, formal system is going to say, yeah, we know how to do it. There are these things, they are verifiable, and we have tests. That's basically what the formal system needs to do. So how do we formalize that? Well, we are going to have to introduce another axiom because we didn't say anything about verifiability before, so we need to say that these things exist. And again, conceptually, a verifiable statement is a statement that, if true, can be shown so experimentally. We have a test, and we can use this test to show that these things happen experimentally. Now, we're going to talk about tests later, but the point is that the tests are not going to enter the formal system because we tried, and it's a mess, and it doesn't add anything. The only thing that we need to do in the formal system is saying that in each logical context, there is a subset of statements that is verifiable. That's what we need to say. And we need to say that every certain is verifiable, if every possibility is verifiable, and that two statements that are equivalent, right, that they're true in all the conditions or false equally in all conditions, those, if one is verifiable, then the other one is verifiable, because you can sort of inherit the test. And so, surprisingly enough, that's all we need to say to bring these into existence, which is much less complicated than having to bring in the formal system the experimental test. But we have to have the experimental test then in the back of our mind because we need to talk about the experimental test when we do the justification. We're going to have axioms, and we need to say at the back of our mind what exactly in the informal system mean that we have these tests and what it means for something that to be verifiable exactly. So the new axiom to bring the idea that statements are experimentally verifiable. And essentially we have this dichotomy. We have the statement that can be true or false, and we have an experimental test that can succeed, that can fail, and whose result can be undefined because it does not terminate or because it doesn't apply in these conditions, and so on. So there is a result that could be undefined. And while the truth and the falsehood of the statement is always well defined, the output of the experimental test is not. And it's the interplay between the test and the statement, these two things, that actually gives us all the structure that then goes into topology, goes therefore in differential geometry, or that. It's all about the tests, and this is the beautiful thing. At a fundamental level, all the mathematical structure that we have on top are all about this. So something is verifiable then if there is a test that always terminates successfully if the statement is true. So in general, it could be that the statement can be true, but we're never going to be able to verify that it's true because test does not terminate, it does not verify, it's not well defined and so on. But if the statement is verifiable, then we're guaranteed that at some point the statement will end and will tell us, yes, it is true. Note, we are not saying when, so we say infinite time, and of course this finite time could be 1 second, 1 hour, 1 year, 20 years. We are very vague about that, so the important thing is that it's finite time. At some point you wait like this, and then at some point you're gonna see that the test succeeds. You don't know when, but at some point will succeed if the statement is verifiable and if the statement is true. If it's false, it could fail right away, or it could never terminate. So something like there exists extraterrestrial life, right? We put the telescopes in various directions, and if we find experimental life, then we stop and we say, we declare at Alpha Centauri there is experimental life, we're good. And if we don't find the evidence, then we keep looking, because absence of evidence is not evidence of absence. And so in that case, we would have a statement that we can assume it verifiable because at some point we are going to put the telescope in the right direction and we're going to see the life. Or if we don't find it, then we never end, we keep continuing. So the statement might succeed, and it's succeed when it's true, so it's verifiable, but it's not falsifiable. It never ends in the negative case. And so these are the type of things that this structure is going to be able to capture. And as I said before, the tests are not objects in the mathematical framework, because defining the test formally is cumbersome, and seems to be that capturing which statements are verifiable is high enough. There's a sort of circular problem if you try to define formally what is testable, because you can only know what actually is testable in a practical way only if you essentially know the laws of physics, because you need that's going to tell you what you can test and what you cannot test ultimately, because you need physical processes to be able to make the correspondences. But then it can't be that to define the most fundamental object in the physical framework, you need the end goal, which is the laws of physics. So that's sort of the thing that doesn't work. So it's just better to say the formal system does not know what the tests are. Formally, only thing we do is we tag which statements are verifiable. And again, the other curious thing is that we only need to tag the verifiable statement, and all the other conditions of test termination in the negative or the undefined can actually be determined from only knowing what the verifiable statements are and the logical relationship between all the statements. It turns out that that's the only thing, and since that's the only thing that we axiomatize and find everything else as definition, because we said we want our axiom to be to have very, very narrow let's say content, because that's the tricky bit. That's a more delicate, that's where we can be wrong in a way that the formal system is never going to catch. So we want our axiom to be very, very fine, that sort of have very little surface. Okay, so now we have to convince ourselves that this makes sense. Certainty as impossibilities are defined to be true or false, right? So the certainty is always true and the impossibility is always false. Therefore, a trivial test that always succeed and always fail will satisfy those ideas of termination. You know, something always succeed and it's a certainty. Something always fails is an impossibility. So those are sort of the trivial tests, and that's why we can always say, oh yes, those things are verifiable. They're verifiable in the sense, in the context of we declare them to be true and to be false. So another way to think about it, to see whether they're true or false, we look at our definitions and we see that by definition are true or false, and so they're verifiable in that sense as well. Now, the other thing that we are saying is that if two statements are equivalent, then the termination conditions on one test and the other are the same, and therefore we can reuse the same test. And this is why we say that statements equivalent to a verifiable statement is verifiable. The idea is that they always terminate in the same condition. So if I have a test that is always terminates successfully if and only if one statement is true, and this statement is true and only true whenever the other statement is true, then I can use the test to find all these statements, to test all these statements. So we are good, and so these elements are fully justified. And so again, if we look at our example of logical context, now not only we have this relationship, but we can tag in green all the statements that are verifiable. So something like the certainties and the impossibilities, we said they are verifiable. Something that has an error bar, like it's less than 10 to the minus 13 is verifiable. Something that is greater than 10 to the minus 13 is also verifiable, but the fact that it's greater or equal, that equal part, it's what the problem is, because saying that we're going to be able to verify the equal, we'll basically be able to say that we can measure that with infinite precision. And so on. So this is basically the general ideas. And if you have studied topology, you can see, oh, these are surprisingly enough open sets in the space, and that's exactly what's going to happen. The verifiable statement become open set in the topology, which we're going to see in another video. But let's see why and how this all works. So the first thing that should be clear is that the negation of a verifiable statement is not necessarily a verifiable statement. Because if we have a statement and it's test, then it's verifiable. So it always succeeds if the statement is true. Making the negation, it basically means inverting the false with the true and the true with the false. But this means that we are also inverting the test condition. So now this was undefined when it was false, and now it can be undefined when it's true. And so now this does not satisfy the fact that this is a verifiable statement. It's falsifiable, right? Because every time that it fails, this is false, but it's not verifiable. So just running the test and exchange succeed with failure, the problem is that it switches the termination condition, but it doesn't change the non-termination condition. And so this is one of the first results, is that the logic of verifiable statement does not include the negation. What does it mean? That the negation of a verifiable statement is not necessarily a verifiable statement. It's still going to be a statement, it's just not going to be verifiable. So we can't do negation. Now, we can define a falsifiable statement as a falsifiable statement is something where the test always ends with failure when the statement is false. So this is essentially the dual of a verifiable statement. And note that formally, falsifiable is defined to be the negation of a verifiable statement, right? And this is how we are reducing the number of primitive concepts, right? A falsifiable statement is a statement that, if false, can be shown to be so experimentally, but formally we're saying that as if falsifiable, if its negation is a verifiable statement, right? So these two things are slightly different. They're not exactly the same. And then what we do in the justification of this definition, we have to show that this is the case. That if we can show that something is experimentally falsifiable, then it is the negation of a verifiable statement. And this is how we do it. Suppose that so we have a statement S and not S, and suppose that not S is verifiable, right? So if there is verifiable, then there is a test that always succeeds if it is true, and then it fails and it's undefined if it's false. Now from E, we can construct this test that switches success with failure. Now, whenever we had failure, right, we run the test. If it fails, it returns success, and if it succeeds, it returns failure. So basically, it's like the same conditions, except we're going to have success and failure. And now what happens, look at this. We have whenever the statement is false, we have a statement, we have a test that always fails in finite time. And so if the negation of a statement is verifiable, then it's the same thing that the statement is falsifiable, right? So we sort of bridge the gap between these two little definitions. This is exactly what we want justification to do, to start with a more common sense way of defining things, and then use the formal system in a way to sort of show equivalence. Okay? And now we defined what a verifiable statement and a falsifiable statement is, and now we can define a decidable statement. And a decidable statement is a statement that can be shown to be either true or false experimentally. The tests always succeed. And now formally, we don't know what tests are, so we're going to say that a statement is decidable if the statement is verifiable and the negation is verifiable. And then we're going to have the decidable statement. So again, this is what we want to show, that the test always terminates both in the true and the false case. And again, note that formally we have done things a little bit differently, because again, formally we don't know about tests, we don't know what means to be shown true or false, and so now we're going to have a justification and show that these definitions are equivalent. So we can imagine that if S is verifiable, we are going to have a test that always succeeds, guaranteed to succeed in finite time if the statement is true. And of course, we have no guarantee for the false. And when if we have the negation of S is being verifiables, we have another test that succeed when this statement is true and we don't have no combination on condition on the failure. And then we want to show that given these two tests, we can construct a test that always succeeds and always fails. And again, now we have the problem, these tests might never end. So, right, so this ends only in this condition, this only ends in this condition. Now we have to stitch these two things together so the things always ends. So we were able to sort of ignore when one of these two tests gets stuck. So this is how you do it. And this is, you make this statement, that this test that works like this. You initialize n to 1, they say 1 second. And so you run the first test for 1 second. If it succeeds in 1 second, then you return success. If it does not, if the other tests succeed in 1 second, then you return failure. Now, of course, you haven't, you might not have reached the success, neither these tests might reach success in 1 second. So what you do is that you increase n, and then you go back to 2. So you run for 10 seconds or an hour. And you see whether one ends in 1 hour or the other one ends in an hour. If none of them end, then you do it for 2 hours, and then 3 hours, and 4 hours. At some point, since you're guaranteed success in finite time, at some point you're gonna hit the appropriate amount of time to make either this or this end, and you're gonna be able to quit. Because either this part is true, either this statement is true, and then this is going to succeed in some arbitrary time, but still finite, or this other test is going to end in some time, and so one of the two tests is going to end, and so this test at some point will end. So if S and not S is verifiable, then you can sort of stitch together this statement, and then it's going to be true that the statement can be shown to be either true or false experiment. Right? So this is the type of thing that we have in the justification. You see, they kind of feel like proofs, but they're not really formal proof because none of this is done in the formal system. And of course, they still feel messy anyway because this is sort of an abstraction. We're still working with abstraction, right? We're never going to construct tests like this, but again, this justification is to show that the formal system is actually closed and makes sense. So we have this, and of course, certainty and possibility are decidable statements because they always are going to be terminating. Both, since one is the negation of the other, then things are good in the formal system. Now, the idea is that before we saw how we could define ands, ors, and not in terms of the truth table. And now we want to understand what type of operations we can do on verifiable statement and still guarantee that the output is a verifiable statement. So this is where, again, we have to put axioms. There is no way to prove because the tests are not themselves in the formal system. So we need to bring in results, again, using, creating this pseudo-proof justification. So one of the things that we want to show is that if we have two statements, actually finitely many statements, and we do the conjunction of them, then the conjunction is a verifiable statement. And conceptually, what you do is you run all the statements, and if they all succeed, they're all going to succeed in finite time, and therefore you have verified that the end of all of them succeed in infinite time. The only problem is that this conjunction has to be finite, because if we had infinitely many statements, right, and we have to run them all, we're not going to be able to run them all. We can only run finitely many statements that finish in finite time and still be finite. Otherwise, we would need infinite time. Now instead, let's say that we have a disjunction, right? With the disjunction, in principle, we can do the same. We can imagine of having all these statements and then test them one by one. And then in this case, we only have to check that one test terminates successfully. So as long as one of the tests in the sequence terminates, then we're guaranteed and we can go away. But the issue is that we have to be a little bit clever again to show that this can always be done because, again, the test might be stuck. And so I can't just wait for the first test to terminate to test the second, because otherwise I might never test the second. So again, we can do something similar of what we said before. We initialize n to 1, and then you run the first n tests for n seconds, right? So you have 1, so you run the first second for first test for 1 second, and if you succeed, you just return. Chances are it does not, then you increment n, and you're not going to just run the first test for 1 second, you're going to run the first 2 tests for 2 seconds. So you increment the number of tests and the number of time. If you don't terminate, then you go back and you run 3 tests for 3 seconds and so on. And the strategy is, if you do this, you are going to run essentially an arbitrarily large, at some point you're going to run all the tests for an arbitrarily large amount of time. So if one of the tests is going to succeed, then you're going to find it and you're going to run it long enough to be able to succeed. So you're guaranteed that if one of the tests terminates successfully in finite time, you're going to find it and you're going to run it for sufficiently long time and you're going to be able to terminate. Now, of course, this only works if you have countably many elements, because again, here we are going through always finitely many, and at some you can only explore countably many with this process. And so that's where we're limited. So we have the axiom of countable disjunction verifiability. We can only verify, we can be guaranteed that we can verify the countable disjunction of verifiable statements. And if we look at the decidable statements, now this is a proposition and not an axiom, because we can actually prove that if we have a finite conjunction or a finite disjunction of decidable statement, then the resulting statement is actually a decidable statement as well. What happens is you use essentially De Morgan rules, and you can transform the negation of the and in the or of a negation and vice versa. So from the determinability of the ands and the or, you can sort of deduce the termination condition for the negation. And since you're going to be able to do both, because you start with decidable statements that are both the statement and their negation are verifiable, you can use this rule and prove this here. But this sort of makes sense at an intuitive level, so we don't even have to go and prove this very formally. So this is essentially how you're going to have different algebras depending on the set of statements that you're looking at. So if you are looking at all the logical statements in our context, then you can do negation, you can do an arbitrary conjunction or an arbitrary disjunction. You can do these things however you want. We said we have a complete Boolean algebra, so we don't have a problem. If we restrict ourselves to the verifiable statements, then we don't have the negation, we only have finite conjunction and we have countable disjunction. And this algebra now is no longer the Boolean algebra, it's what is called the Heyting algebra. It's something that people use in intuitionist logic. And this again is there to capture the fact that we have this finite time verification. But again, this is embedded in this other algebra, so there is some interplay between the two. And then, of course, we have the algebra of decidable statement, where negation is allowed again, because both everything terminates, and you can do finite conjunction and finite disjunction, so it's a different thing. There is also another algebra that you can put inside here, which essentially corresponds to all the statements that have a test, and in that case, you are allowed to do a negation and countable disjunction and countable conjunction, and you always have a test, a statement that has a test. We call those theoretical statements, but you absolutely have no condition on the type of termination that you have. They might never terminate, so they can be verifiable, falsifiable, or any mess of things. And that algebra is actually what's going to become the sigma algebra of these spaces, and it's the things that you define probability theory on, right? The idea is that you define probability on statements for which you have a test, and then the probability is going to tell you essentially the falsehood or the chance of being false or true, and of a statement that actually have a test. But again, the test it's not, you're not guaranteed to have good termination conditions on those tests, but in principle you can assign the probability. So this is essentially how it works at sort of a conceptual level. And but now we're going to be interested in finding sort of pieces of this that represent essentially the elements that they actually want in a physical theory. So that this is basically the logic, okay, but what are the things that we are actually going to describe? When we talk about position, velocity, when we talk about these physical concepts, how can we understand them in terms of this framework? Well, so the idea here is the first thing that we want to ask to have a manageable, let's say, set or subset of statements. And we are asking what is the largest set of verifiable statements that it makes sense to consider, right? Because you can imagine to have like uncountably many statements. The problem is that can we actually explore all these things or not? And how can we combine them? Like what is a good set that makes sense to get together? And so one of the things that we note that even assuming an indeterminate amount of time, we can only run up to countably many tests. Because to any test, we can at most give a finite amount of time, and therefore we can only run countably many tests that for a finite amount of time each. So more than that does not make sense. But what is interesting is that testing some statements implicitly tests all other statements that can be expressed as a function of the previous one. So for example, if we test S1 and S2, well, we're kind of implicitly testing S1 or S2 and S1 and S2, because what we learn about this statement is enough to determine the conjunction and disjunction. So what you're really looking is for a set of verifiable statements whose truth can be verified by running countably many tests. So countable many truths are at most what we can find experimentally. We say this is true, this is false, this is true or false, and so on. We can go on forever, or so we imagine. And that's as much as we can do. But there are more than countably many statements that might depend on that truth. So how do we formalize that? Well, given a set D of verifiable statement, we say that B, a subset of D, is a basis if the truth values of B are enough to deduce the truth values of all the sets. Again, formally means that all the elements of D can be generated from B using finite conjunction and countable disjunction. So we take some element from B, we do all the countable, all the conjunction, disjunction of that statement, all the other statements, and so on. We create all these big expressions, and then we say, okay, that's going to be if we can generate all the statement in D only using the statement in B and these operations, then we only need to test B. We don't need to test the full D, and D is essentially equivalent as verifying B. And now, since we can only test countably many things, we define an experimental domain essentially to be formally a set of statements that is closed under finite conjunction and countable disjunction. So basically, it gets all the statements that can be deduced one from the other, and includes the certainty, the impossibility, and a set of verifiable statements that can be generated from a countable basis. So basically, D is a set of verifiable statements that can be fully tested and verified by running countably many statements. Therefore, it can be verified in an indefinite amount of time. And this forms a good group of statements to look at. And so if we are going to look at statements of position for a particle, these will form a domain and so on. So this is sort of what we're going to be looking at. And the idea, the consequence we have is that every physical theory, at the end of the day, must be fully characterized by an experimental domain, because it must be evidence-based. So all the statements must be related to verifiability, and therefore, and so this is the best we can do, then this is, every theory has to fit this, because this is the best we can do. So all its contents, all the contents of the physical theory must be expressible in terms of verifiable statement, and a theory must be fully explorable with countable set of statements and of tests, because otherwise it's not connected to experimental evidence. There is too much. We're never going to be able to say anything about the full theory. And so this is sort of how it works in your head, or in my head. There is this logical concept that have all the statements, so things that are verifiable, not well-defined experimentally, not not explorable experimentally. And then within the logical context, you have a subset, which are the verifiable statements, things that we can use to define the connection to the experiment. And from there, we really have the correct notions. And then within the set of verifiable statements, we can find experimental domains. So we're going to have the experimental domain of velocity for a particle. That is going to be all the set of things that we can measure about the velocity. Oh, it's within this, it's here, within this interval, it's not within this interval, and so on. So there are all these types of statements. We're going to have something for position and for velocity. And a particle state is going to be the domain that is generated by all the statement of position and velocity. So you're going to have things of position and velocity. The position of the particle is within this interval, and the velocity of the particle is within this interval, and you get all of this. You're going to have an experimental for time, you have an experimental domain for energy, and the physical theory is what's going to be establishing relationship between these experimental domains, right? So all that we need to do is all of this. And you say, but Gabriel, putting all these like weird things in new math, and it turns out that this is not new math, and this is kind of the point. All these experimental domains, they map to topological spaces, and each experimental domain, the verifiable statement in an experimental domain are the open sets, and the points of that space are the min terms of the basis, because they represent these lines in the table of things that can happen. And so all of this maps exactly what we are already doing at a mathematical level in all physical theories. We have a topology, and the topology tells us what is verifiable, and when we make the limits, we're making limits as defined in the topology, which means that our limits are exactly a verifiable statement that becomes smaller and smaller and smaller and pick out more and more refined definition. So all of this, it's a construction that we have that starts from a very general consideration, but recovers things that are actually we're already doing, and it actually makes it a lot more precise, both from the conceptual and the mathematical level. It tells you what type of topological spaces we can have, and which kind of relationship between topological spaces we can have. And I'm going to explore this in a different video, because this is already too long, but the point is this that I want to make, that all of this mathematical structure that we have in physics is really derived from these ideas, and they are derived from the idea that we have experimental verifiability. So you have this algebra statement that possibly it's infinite and intractable, but the part that is experimentally accessible is more constrained, and it's a lot more tractable with techniques that are similar to what you actually have in computer science, because computer science cares about finite time termination of computational processes, or in intuitionist logic, where in constructive logic, where you do care about whether you actually can write down proofs or can actually construct objects, which again, those require finitely many symbols. So there is sort of a flavor within all of this that takes ideas from there, but it sort of reshuffles them in a way that is what we need for science. And I know that it's what we need for science, because at the end of the day, that's what we already have a lot in the math. So the point of all of this exercise is not only to have a clear idea of, that there are these elements, but how they come about and the fact that we can see them more clearly, how they are constructed. And with that knowledge, we can see that some of the things that people try to do in the foundation of physics may not make sense, because if I am talking about hidden variables in some interpretation of quantum mechanics, you have hidden variables, meaning variables that exist but are not experimentally accessible. And the issue is that people use these variables, again, like real numbers and so on, in the same way, using topological spaces. But we saw here the topological spaces, these things are tractable because they're experimentally accessible. Things that are not experimentally accessible and hidden variables are defined to not be experimentally accessible, they don't have this constraint. They could be a lot more complicated, and there is no reason why they should follow this same pattern and why we should be able to characterize them in the same way. There's really no reason. And so if somebody is working with these notions and trying to create physical theories of these hidden variables, personally, I think they're using the wrong tools, because these tools are not designed for that. There is no reason. You don't have that level of control. These things could be horribly complicated in ways that our finiteness, our finite being might not even be able to grasp or manipulate and so on. So this is where I think it's important to really go at the foundation and understand why we have this mathematical abstraction, where they come from, and what is their physical motivation, because otherwise we don't know what we are doing. We are going to use these mathematical abstractions saying things that might be right and might be wrong. We don't know because we haven't done the due diligence. So that part of my project's Assumptions of Physics and this approach physical mathematics is really to go in and get into the details so that we actually know what we are talking about. And I think that's important if we want to be able to construct physical theories that sort of go beyond the physical theory that we currently have. So thank you again for your attention. If you are interested in this sort of research, you can subscribe to my channel. I have another channel where I actually go more in details of the active work that we're doing, if you're interested to know more or collaborate or see what we're doing. And otherwise, there is also a link to my website if you want to know more about the project. And thank you again if you are still here for your attention, and see you next time.